let's take a few minutes and look at some different types of diffraction. At the end of this video, we'll be able to talk about a field called spectroscopy, which is determining the different wavelengths of light and the different chemicals within stars. So here's a fun example of a diffraction pattern using a disk. Now, back before Thomas Young did his double slit experiment, there was a debate about whether light was actually a particle or a wave. And Thomas Young's experiment resolved that and said, yes, it is a wave. But before he came along, there was this debate where there was a scientist who argued that, yes, light is a wave. Well, there was another scientist there by the name of Poisson who argued it can't be, because if light were a wave, then it would follow this path, it would diffract, and then you'd have constructive interference right in the center of the shadow of that solid disk. He set up the experiment and said, you see, there isn't a shadow, or there isn't a bright spot in the middle, and so light can't be a wave. Well, we kept going at this study for a few years after Thomas Young showed that yes, light is a wave, so we started working on this. And sure enough, we got the experiment just right, that we got the light to create a shadow on a view screen behind, and we got it just right so that a bright spot appeared right in the middle of that shadow. And so, since Poisson was the scientist who doubted it, we affectionately call that Poisson's dot. So anyway, there's a form of diffraction that's interesting and really fun to see. Here's another interesting one where you have light that passes through just a single slit. Let me redraw that so it's a little bit nicer. There we go. So light comes through and passes through a single slit. Let me get a different color. And because of diffraction patterns, this is how we saw it before. But if you get the space just right, essentially what you have is one wave from one side, one wave from another side, creating a constructive interference pattern and other minor constructive interference spots along the side as well. And you end up with a pattern that looks just like this graph, where you have a very bright spot in the middle and then some more bright spots a little further away. Now notice that the first dark spot, the first area of destructive interference, is a distance of lambda over d, which is the diameter or the width of the slit. And this x-axis, excuse me, sorry, hit a button and went to the wrong page. We're back. So the x-axis here is sine theta. So in this case, you have sine theta. It's going to be at a value of lambda over d, and that's going to be a region of destructive interference. Well, you get it again at 2 lambda over d or 3 lambda over d, so we're going to just use the m number here again. Sine theta is equal to m lambda over d. Simplifying that, that means d, the diameter or the width of the slit, times the sine of theta is going to equal m lambda, where m is plus or minus 1, plus or minus 2, plus or minus 3, so on. But this is for the minima. In other words, these are the regions of destructive interference, or for the dark fringes. Okay, that's the single slit experiment. Here's another interesting diffraction experiment that we can do. This is called a diffraction grating. A diffraction grating consists of a large number of equally spaced narrow slits or lines. So we saw a single slit, we have seen the double slit, and now we're seeing multiple slits. And it turns out this creates quite an interesting effect. It's the same as the double slit experiment, where you get multiple bright spots on the wall. But with the double slit experiment, you can get, the bright spots are only like millimeters or micrometers apart. But with the diffraction grating, they turn out to be much wider apart. Depending on how far away the view screen is, it could be from a few centimeters to even meters apart. Now, I'll show you in the next figure why this happens. But yes, in this figure you see the laser coming in from the left, hitting the diffraction grating, and then all of a sudden the laser splits into 3 beams, or diffracts into 3 beams. So that on the wall you see 3, looks like we have 5 very distinct spots on the wall. You have your laser down here on the bottom of the screen. There's your diffraction grating. 1, 2, 3, 4, 5 bright spots on the wall. So the way that this happens is has to do with the number of slits you have. On the left, in the figure on the left, you have basically what looks like the double slit experiment. But as you add more slits, you start creating a combination of constructive and destructive interference patterns. So some of those some of those maximum points become smaller. They become less, the amplitudes decrease significantly. And so there are only certain regions where you actually do get constructive interference, and so the spacings between maximum points are further apart. Now the interesting thing is that the equation is the same as it was for the 2-slit experiment. Sine theta is equal to m lambda divided by d, which if you multiply by d, you get d sine theta equals m lambda, same as it was for the double slit experiment. And d would be the distance between any 2 lines in your diffraction grating. Now, in a diffraction grating, this is what you would see. Right in the center, all light is going to create a maximum point right in the center. And so no matter what the wavelength is, they combine right in the middle and you get a bright white line in the middle. But then blue light is going to diffract at 1 rate because, remember, this function depends on wavelength. So if you have a blue light here, you get your m equals 1 for blue light here, m equals 2 for blue light here, same on the other side. And then, if you're lucky, you'll get an m equals 3 further to the right. Now, at the same time, if red light is passing through the same diffraction grating, you're going to see the first red line a different distance away because you have a different wavelength, you're going to have a different angle. And so you get your m equals 1 for red light here, m equals 2 for red light there. On the other side, m equals 1, m equals 2. Now, if we have a light source like the sun, which has multiple wavelengths, nearly all the wavelengths, then you're going to end up with a full spectrum with violet on the left, red on the right for your m equals 1, and then you're going to see it again for m equals 2. Well, this leads to the interesting field of spectroscopy. Now, remember that you have a, we'll do it with red light. So you have a light source, say a laser, that goes through a focused column to block out any other light, and it hits this grating. Well, then you're going to have your m equals 0 line, and then it's going to diffract in different directions. Each one of these is m equals 1, and you may get another m equals 2 out here. And you have this little telescope. Let me do this one in blue. You have this telescope here which can move back and forth. And you look through that telescope until just the right point that you are looking directly at the m=1 line. And by doing that, you can very accurately measure the angle of that diffraction. And then following the equation of diffraction, you have the angle, you know the diffraction of the distance between the spaces in the grating, and m is just equal to 1 in this case, and so then you can actually calculate the wavelength. So what we've done is we've found light sources such as stars out in the sky that become a source, and look at them very closely through a telescope. That let that light through the telescope come into the collimator, hit a diffraction grating, then have this rotating telescope. You can measure exactly the wavelengths of light that the star emits. So using this is the equation I just showed you. Just solve for wavelength. This is how, having solved for wavelength, this is how you can calculate the different wavelengths of light that are emitted by a certain light source. Well, atoms and molecules can be identified by the types of light that they give off. For example, here at the top, you have what's called the spectrum of light emitted by hydrogen gas. So you take hydrogen atoms, you excite the electrons in the hydrogen atoms, and that process results in the release of photons or light. Which light waves can we get? Well, you get a red light, you get a couple of blue lines, and then you get purple lines. Those are the main colors that are emitted by excited hydrogen atoms. Likewise, mercury, you get a violet, you get a band of blue light, you get green, and you get a couple of yellow, handful of red. And sodium's an interesting one. But with sodium, the reason why sodium is so interesting, there are only these two lines in the yellow that sodium releases. That's the only visible light we get from excited sodium atoms. Now here's why it's interesting. When you look at the sun, this is the solar absorption spectrum for the sun. You see these gaps? These gaps are there because there are certain atoms which emit those wavelengths of light, but they're not present in the sun to emit those wavelengths. For example, here, notice there is a gap, or excuse me, two gaps that line up perfectly with the sodium. But those wavelengths aren't there in the solar spectrum, which means the element that makes those two wavelengths, sodium, is actually not present in the sun. And so we can use spectroscopy to actually look and see what any gas, including the gases within a star, what gases are present, so we can find out what stars are made of.